It's a completely ordinary morning. The sun is about to rise, just like it has for 4.5 billion years. But this morning, something impossible happens. In less than a second, our sun is gone, replaced by a different star entirely. Not a similar one, not a slightly bigger one, a blue supergiant, nearly 100,000 times brighter than the star we've always known, sitting in the exact same spot, the exact same distance away. Nobody on Earth notices the instant it happens. Light still takes 8 minutes to reach us. But in 8 minutes, the sky above every single person on the planet is about to change forever. And nothing that follows will be survivable. To understand what's coming, you need to understand the scale of the difference. Our sun has a radius of about 700,000 kilometers. Rigel's radius is roughly 78 times larger. If you placed it where the sun used to be, its surface would swallow the orbit of Mercury completely. In terms of mass, Rigel weighs in at around 21 times the sun's mass, enough to fundamentally rewrite the gravitational rules of the entire solar system. But the number that matters most for Earth is luminosity. Rigel puts out roughly 120,000 times more light and radiant energy than our sun. Earth isn't built to survive a star this bright at this distance. Nothing built around a calm, stable, average-sized star ever could be. 8 minutes after the swap, the first photons from Rigel finally reach Earth. On the side of the planet facing the new star, the sky doesn't gradually brighten like a normal sunrise. It detonates into light almost instantly. Anyone looking toward the horizon in that moment experiences something no human being has ever survived. A flash of blue-white light, roughly 100,000 times more intense than anything the retina evolved to handle. Within seconds, temperatures on the exposed surface begin climbing far faster than any natural weather event in Earth's history. This isn't a sunrise anymore. It's closer to standing at the edge of an explosion that simply refuses to end. 15 minutes in, looking anywhere near the sky has become physically impossible. The light alone is enough to damage human eyesight in seconds. But the real danger is invisible. Rigel pours out enormous amounts of ultraviolet radiation, far beyond anything the sun ever produced. Earth's ozone layer, built up over billions of years to filter exactly this kind of radiation, was never designed to handle a source this powerful. It doesn't just get overwhelmed, it gets destroyed, torn apart by photochemical reactions happening faster than the atmosphere can rebuild it. Within minutes, the planet loses its only shield against ultraviolet radiation. Every surface exposed to daylight is now receiving a dose of radiation no organism on Earth has ever evolved to survive. 1 hour after the swap, the exposed side of Earth is absorbing a radiant energy flux roughly 100,000 times greater than normal. Surface temperatures on the daylight side are climbing at a rate that would normally take centuries of climate change to reach, compressed into 60 minutes. Deserts begin to glow with heat shimmer visible from orbit. Forests start igniting spontaneously, not from any spark, but from radiant heat alone crossing the ignition threshold of dry wood. Coastal waters near the equator, closest to the star's most direct angle, are already measurably warmer than any recorded ocean temperature in human history. And this is still just the first hour. The planet hasn't even begun to show its worst symptoms yet. Astrophysicists modeling this scenario point to real, measured data. Rigel is a star we've actually studied in detail, roughly 860 light-years away, in the constellation Orion. Its surface temperature sits at around 12,000 Kelvin, more than twice as hot as our sun. Combined with its enormous size, that translates directly into the staggering luminosity output driving this entire catastrophe. Researchers modeling stellar replacement scenarios note that no planet orbiting this close to a star of this class could retain a breathable atmosphere for more than a matter of hours. The habitable zone around a star like Rigel doesn't begin anywhere near 1 astronomical unit. It starts hundreds of times farther out than Earth's actual orbit. By every physical measure available, Earth's position around this star is not survivable. 6 hours in, the daylight side of Earth has crossed a threshold there was never any coming back from. Ocean surface temperatures near the equator reach the boiling point, and vast columns of steam begin rising into an atmosphere that's already failing to hold itself together. The intense radiation isn't just heating the air, it's stripping it away entirely, accelerating molecules in the upper atmosphere until they simply escape into space. Satellite-style views from orbit would show something unprecedented, a planet visibly venting its own atmosphere into the void, a faint comet-like tail of gas trailing off the side facing away from the star. Earth is no longer just overheating, it's beginning to disappear. What's happening to Earth's atmosphere has an actual name in astrophysics: hydrodynamic escape. Under normal conditions, gravity holds gas molecules close to a planet's surface. But when radiation input becomes extreme enough, molecules in the upper atmosphere absorb so much energy that their velocity exceeds the planet's escape velocity entirely. They don't just drift away slowly, they stream off in a continuous bulk outward flow, like steam escaping a kettle that never stops boiling. This exact mechanism has already been observed on exoplanets orbiting close to bright, hot stars, worlds astronomers call evaporating planets. Earth, under Rigel's light, would join that category almost immediately. The atmosphere isn't being blown away, it's boiling off, molecule by molecule. 24 hours in, there's no longer anywhere to hide. Earth's rotation used to be humanity's greatest protection, a built-in mechanism that gave every point on the surface 12 hours of relief in darkness. But that protection assumed a stable atmosphere carrying heat evenly around the planet. Now, with the atmosphere itself collapsing and streaming into space, the normal heat circulation breaks down completely. Superheated air from the daylight side surges directly into the night side in violent, continuous currents. Hurricane-force winds strong enough to level structures tear across what used to be the safe half of the planet. There is no more nighttime relief. There is no more day and night. There's only one continuous planet-wide catastrophe now. As if the radiation alone weren't enough, a second, slower catastrophe is already underway. Earth's orbital velocity was calibrated for a star roughly 1 solar mass. Rigel is 21 times heavier. The same orbital speed that kept Earth perfectly stable around the Sun is now far too slow to maintain a stable orbit around a star this massive. Physically, this means Earth's path is no longer a closed, stable circle. It begins a slow inward spiral, drawn gradually closer to the star with every pass. It's a slower death than the radiation, measured in days rather than hours, but it's just as certain. Even if some way existed to survive the heat, the orbit itself would eventually finish the job. 3 days after the swap, the spiral has become impossible to ignore, even from a purely visual standpoint. Each pass around the star brings Earth measurably closer than the one before. What used to be a stable, nearly circular orbit has become a slow, deliberate descent. And the closer the planet gets, the faster that descent accelerates, since gravity only grows stronger with proximity. By this point, what remains of Earth's atmosphere streams behind it in a continuous, glowing trail, making the planet itself look less like a world and more like an enormous, doomed comet falling toward a star far too massive for it to ever have belonged to. When researchers model this kind of scenario, they arrive at an uncomfortable conclusion. Earth would be facing not one, but 2 completely independent extinction mechanisms running in parallel. The radiation and heat alone would end the biosphere within the first day. The orbital decay alone, given enough time, would end the planet itself. Neither mechanism depends on the other. Even in some alternate scenario where the atmosphere miraculously held together against the radiation, the slow gravitational spiral would still be running in the background the entire time, guaranteeing eventual destruction regardless. Astrophysicists studying stellar replacement scenarios note that this combination, instant radiation catastrophe plus inevitable gravitational decay, is what makes swap scenarios so much more severe than a simple dimmer star or no star at all hypothetical.
2 weeks after the swap, what's left of Earth crosses the final threshold. The tenuous outer atmosphere of Rigel itself, a star so enormous its surface has no sharp edge, only a gradual thinning into space, begins to make contact with the planet's remains. Friction against this outer stellar material starts tearing away what little structure the planet has left. There's no dramatic single moment of impact. Instead, there's a slow, continuous disintegration, layer by layer, as Earth's remaining mass gets folded into the star it was never meant to orbit. Within days of first contact, there's nothing left resembling a planet at all, only debris gradually absorbed into Rigel's outer layers.
Taking stock of the full scenario, the outcome for the inner solar system is total. Mercury and Venus, already close to the Sun's original position, are consumed almost immediately by Rigel's enormously expanded surface. Earth, as we've just seen, is destroyed through a combination of radiation and gravitational decay within about 2 weeks. Mars, farther out, survives the initial radiation pulse, but finds itself now sitting closer to the habitable zone of this new, far brighter star than it ever was to the Sun's, though still likely too far and too thin atmosphere to become truly livable. The outer gas giants, ironically, fare the best. Jupiter and Saturn, already positioned far from the swap point, absorb the increased radiation but retain their basic structure, their orbits gradually adjusting to the new stellar mass over centuries.
Here's the part that makes this scenario more than just a thought experiment. Our actual sun isn't going to stay the way it is forever. In roughly 5 billion years, it will run out of hydrogen fuel and begin expanding into a red giant, swelling outward until its surface reaches and likely engulfs Mercury, Venus, and possibly Earth itself. The mechanism is different, a slow stellar evolution instead of an instant swap, but the outcome for the inner planets converges on something eerily similar to what we just walked through. Every star has an expiration date, and every planet close enough to one is, on a long enough timeline, living on borrowed time. Rigel just shows us what that ending looks like, sped up from billions of years into 2 weeks.
In the end, what remains where Earth used to be is nothing more than a faint trail of debris, slowly settling into orbit around a star it was never supposed to know. Rigel continues burning exactly as it always has, indifferent to the small blue planet it briefly consumed. Somewhere else in the galaxy, other stars are living out their own lifespans right now, some stable for billions more years, others far closer to their own violent endings than anyone watching them realizes. It's a strange kind of comfort, knowing our actual sun still has roughly 5 billion peaceful years left to give us. If you enjoyed imagining just how fast paradise can end, subscribe to the channel so you don't miss the next What If.